Hello, YouTubers. You just missed 11 minutes of class, but that was a quiz. So. All right. I have struggled for 24 years to figure out how to best teach Lenz's law. And I think I've done it, but that doesn't change it from being like one of the more difficult things that I'm going to ask you to do conceptually. For those of us that struggle with conceptual stuff, we're going to hate this. If you like conceptual stuff, you're in luck. Because what we need to do is we need to tell you why a minus sign is right here. Okay? And that minus sign in Faraday's law of electromagnetic induction is a reminder of this law right here, Lenz's law. I'll tell you what the law is, and then I'm going to try to teach you how to apply it, and then we're just going to do a bunch of practice, because I think this is something that doesn't sink in until you practice it a lot. Lenz's law states, okay, that, and I'll try to write this out. It's not going to be pretty handwriting, okay? A coil will always fight. That was the word fight. Fight the change in flux through it. Doesn't seem too difficult on the surface, right? Okay? But our universe is built in such a way that when a coil senses a change in magnetic flux, it will immediately respond to that change by fighting it. I think of coils as being like teenagers. Okay? You tell them to do something, and because their brains are malfunctioning, they'll do exactly the opposite, right? Okay? Yeah, what do I mean by fight, right? Okay? It all comes down to a change in flux. So the first difficulty is that we're still sort of grappling with this whole concept of what does it mean to change the flux, right? There's flux, which is BA cosine phi, but we've got to find how it changes, which is often difficult for our human brains to really sort of think about. And then on top of that, we got to figure out what does it mean to fight a change. Like, how do I work against a change, right, in flux? And I'm going to try and explain all of this. Unfortunately, this is going to involve several right-hand rules stacked on top of each other. Because we have magnetic fields, we have responses to those fields, and so like all of your conceptual nightmares are coming true in this one instant. Okay, so let's just hold. I've hopefully scared you enough, right, that you're willing to pay attention. Please just don't give up. You can do this. Okay, you can do this. So let me give you. It's me, so I had to have a 3-step process, right? Something I can always do to make sure that I've got like at least more than 50% chance of getting it right. Okay, and just guessing. So this is the 3-step process that I'm going to use over and over again while teaching you. When you come to me with a question, when I grade the exams, it's going to be kind of like against this 3-step process. Okay. So step number 1. Determine the change in flux. I'll give you details on how we're going to do all this in a second, right? But this is the overview. First step, got to figure out what the flux is doing. Okay? Put that on a t-shirt. 2, okay? Step 2, okay, is you're going to apply Lenz's law. That's supposed to be Z. And then 3, you're going to apply a right-hand rule to step number 2 to get the direction of the induced current in our coil. So 3 very sort of brief statements about this 3-step process that we're going to get into, right, about what's going on. So Let me give you an example. I'm going to step through that example, and then we're going to clarify a lot of the ideas that fall out of this example. Okay? So I'm going to, let's do this. Okay? Let's say I've got a magnetic field pointed into the page. Okay? And we've got a loop of wire. I'm going to draw it like this, a coil of wire. That wasn't a very good coil. Okay. And this, yeah, I cheat all the time. All right. Because I can't draw. Okay. This coil is moving into this magnetic field. I've tried to draw this in such a way that like you can kind of see the box where the magnetic field is, okay? But the coil is partially outside that magnetic field and partially inside the magnetic field, right? And I can't draw the animation, but like the coil started over here on the left and is moving towards the right and will eventually get fully inside the magnetic field and then leave the magnetic field. We got the idea of what's going on here? Okay? All right. We want to find the direction of the induced current in this coil. We can calculate what the EMF will be. We can calculate the voltage and hence the current and stuff that's in this coil. If we could find the numerically, right, the change in magnetic field. So this coil is going to go from 0 as an initial to some magnetic field as a final when it fully gets in, right? So we could find the delta B, the area is not changing, the phi is not changing. So we could calculate that. And if we knew that it took 2 seconds to do that, right, we could get a number. But what we're doing right now is all about this minus sign in this equation. That minus sign is a reminder of Lenz's law.
Is that the fighting?
Yeah, this is the fighting that we're talking about. Okay, so step number 1. How is the flux changing? Is it getting bigger or smaller? Bigger. Why? It went from 0 to something, right? And remember, changes are final minus initial. You compare the final state to the initial state, and here the final state's higher, isn't it? Okay, so I'm mixing my colors right now. I shouldn't do that. So the flux increased, didn't it? However, there's another piece to magnetic flux. Magnetic flux is a scalar technically. But this flux came about because of a magnetic field, and that magnetic field has a certain direction. So the flux is getting bigger, it's increasing, but the field that generated it is pointed into the screen. So in this first step, when you determine the change in flux, you have to decide whether it's increasing or decreasing, and then you have to figure out what direction that magnetic field that's causing the change in flux is pointing. So I usually write just like increase into, increase left, increase out, whatever's happening. Okay. Step number 2, apply Lenz's law. Lenz's law says that a coil will fight the change in magnetic flux. So how do you fight an increasing flux? If flux is getting stronger, what do you do? If I come up to you and I start pushing you and you don't like that, what do? You push back, don't you? You fight the change, right, that I'm applying to you. Lenz's law is the electrical equivalent, right? Here the flux is increasing into. Now, I should say this. The coil cannot make negative flux. Like the coil can't make anti-field or anything like that, right? So the coil, the first word in step number 2 is always the word increase. In other words, the coil is going to make magnetic flux of its own. There's this external flux that's coming from the green magnetic field that I have up here, right? That external flux is increasing in the coil. The coil doesn't like that. The coil will fight the change. But the coil can only make magnetic flux. It can't make anti-flux. So how do you oppose an increasing into if you have to only increase? What direction would you increase your flux? Out. The only other answer is out, right? So if it was increasing into originally, then the coil is going to increase out. In other words, the coil will generate a field inside of it that will be pointing opposite to the magnetic field because of Lenz's law, not because of the field direction. We're going to do a lot more examples. You're going to see what I mean here.
Is that why when you drop like a non-magnetic like thing into like a really big magnet, it slows down?
Yeah, I'm going to do some demonstrations. Okay, so we've established, first step, what the external field is doing to the coil in terms of flux. We've now established that the coil will, to fight that change in step 1, we've established what it's going to do. Step 3 is you apply the right-hand rule to step number 2, the direction you found in step number 2, to figure out the direction of the current in the coil. In step number 2, we discovered that the coil will create magnetic flux pointing out of the screen. We want to find the direction of current in the coil. The coil is making a magnetic field, and we want to know the direction of the current. Is that a handshake or is that a hitchhiker? It's a hitchhiker. There's no force involved here, right? So of the hitchhiker, we've got 2 versions, right? We got the version with the straight thumb, and then we got the version with the, right? Okay, so what shape will the current be if it's a coil? A circle, right? So our current is going to be our fingers, but we don't know what direction the current is. What do we know? The direction of the field, right? So we're going to take our thumb, and which way are we going to point it? Out. And our fingers wrap around which way? Counterclockwise. Left didn't work because at the bottom it would be right. Okay, so step number 3, okay, the answer is counterclockwise. Again, we're going to do this a lot. Well, a lot. We're going to do this 4 or 5 times. Okay. All right, same coil now. I'll draw it in red. That's supposed to be the same coil. You're just going to imagine that it is now leaving. Okay? So what would step 1 be? Do it up here. Step 1, okay? What is the flux doing in the coil? Is it increasing or decreasing? It's getting less, right? It's leaving the field behind. So we know that the flux is decreasing. Okay? What direction is the magnetic field that causes that flux pointing? It's still pointing into. That didn't change, right? The green X's are still pointed into the screen. Okay? How do you fight? Don't say it out loud. Just think. How do you fight a decreasing into if the first word you have to say is increase? Don't say it out loud. Think about it. Okay, now turn to your neighbor and in 15 seconds tell them what you think the answer is. Increase, fill in the blank. Tell your neighbor. Okay, how many of you turned to your neighbor and went, huh? For the 4 people who are honest, thank you. For the rest of you who are lying, okay, right? Yeah, we'll still go over it, right? The question is this. We know the flux is decreasing into. The coil wants to fight that. And the only way to fight is to make or increase flux, okay? So if your flux, which is pointing into the screen, is getting weaker, what are you going to do as the coil? You're going to make into. It's decreasing pointing into. It's getting weaker pointing into. The coil wants to fight the change. The change is a decreasing into. And so the only way to fight that is to increase into. If you are helping your friend push a stalled car, and your friend is falling behind and they're too tired and they can't do it, and you want to maintain the same level of push, what do you have to do? You have to put more effort in, right? The coil fights the change. Everybody wants to concentrate on what the field is. That's not, I was going to say it wasn't important. It is important. It's part of the importance. You have to concentrate on the change. The change is a decrease into. And so the coil is going to increase into. It's going away and it wants to keep it. And so it's going to make more in the same direction. This is the struggle of Lenz's law. Our brains don't do well with changes in things. They do well with identifying things. But how those things change, especially over time, human beings suck at that. Like, we're really bad at gauging things like the strength of the economy over time, right? We don't deal well with climate change because it takes too long, right? And everybody says, oh, isn't this so weird? We're getting rain right now. This was normal 10 years ago, right? Like, our brains, we're designed, we're genetically programmed to concentrate on the tigers that are right in front of us, not the ones that were there yesterday, right? So it's no surprise that this is a struggle for us, okay? So we know that the coil is going to increase into, and now is step 3. Which way do we point our thumb? We follow the direction that we got in step 2. Our thumb goes into, and our fingers wrap around which way? Clockwise. Okay? We can indicate the first one like going with an arrow like that, and then we can do the red one with an arrow like that. Let's, before we do more examples, let's take a step not backwards. Let's look at this from a higher point of view and see if we can't come up with a understanding, even a table of choices, all the possible choices, right, for what flux could be doing and what the response of Lenz's law is. Like, this is just a high level, not looking at a specific example, but what are the possibilities? And what we hope is that there isn't too much of a decision space. We hope there aren't too many choices, right? Because if there are, we give up, we change our majors, we do something else, right? So, what are all the possible choices, right, for step 2? We'll call them step 2 choices. Now, step 2 choices are based on step 1, right? Well, okay, let's list them all out, right? Okay. We can have increase, we'll say into. And what's another increase that we could have? Increase out. Now, I'm using into and out because it's what the example I just did had in it, right? It can be left or right. It can be up or down. But the point is, right, it's going to be kind of one or the other, right? Okay? It's going to be pairs of opposites. So we'll just leave it as into or out. But sometimes the way they're drawing the picture or whatever will change. Okay? But those are two possibilities already, right? Increase into or increase out. Are there any other ways that the flux can change? Okay, a decrease into and a decrease out. Are there any other ways the flux can change? At this high level, where we're simply talking about whether the flux is getting bigger or smaller, the answer is no. You can have increasing in one direction or another direction, or you can have a decrease where it's getting weaker in one of the two directions.
Can we have it stay the same?
Okay, so that's the third possibility, right? So if the flux doesn't change, then the answer is really easy. What's the answer? Zero. There's no current in the coil. There's no direction, right? As an example of that, when the coil is inside the magnetic field, completely inside the magnetic field, still moving, is the magnetic field changing? Is the area changing? Is the angle changing? So this coil goes from a counterclockwise flow as it enters to nothing while it's inside the field to clockwise as it exits.
So like the other day, you put the magnet in, it goes one way, then zero, then
Yeah.
goes out.
That flipping of the thing back and forth was Lenz's law happening. Okay? So the good news is that we really only have 4 choices for the first step, right? Okay? So how many choices do you think we have for step 2? Depends on how you want to think of it. There's 4 choices. Okay? How do you fight an increasing into the page? In all 4 of these choices, you can only use the word increase. Lenz's law states that the coil will fight, but the coil has to generate a field of its own. And that field is what will be fighting the change. Okay? Again, there's no anti-magnetic field. There's no null field, right? It's just another magnetic field that's generated in order to fight the change. So that's why we use increase for every beginning in step 2. If you start step 2 with decrease, you're doing it wrong. Okay? Because step 2 is all about what the coil's doing, and the coil can only make flux. Okay. So how do you fight an increasing into? You increase out. And how do you fight an increase out? Okay, I feel like that one feels normal or straightforward, or yeah, if you think about it, you're like, yeah, okay, yeah, no, I can see that, right? If somebody's pushing me, I'll push back the other way, right? Where it gets a little bit tricky is these decreases, right? And again, this is more like the analogy of you pushing a car with a friend. If they start lessening their force, what do you have to do? Increase in the same direction. So a decrease into will be fought by an increase into, and a decrease out, increase out. Yeah, it depends on how you want to count it. I think of it as 4. Okay? But the good news is that this is the total number of options. Of course, like I said, it could be increase left, right? In which case you would say increase right. Do you see how these are opposites? Right? Okay? So it may not be strictly into or out of the screen. It could be left or right. It could be up or down, right? But the point is you have a template for flux changing in step 1, the external field, and then step 2, what is the coil going to do? And step 2 is Lenz's law. And this little table here captures this essence of Lenz's law, that the coil will fight the change. Not just fight the field, but fight how the field is changing through it. So let's do some more examples. With this in place, okay, let's do some more examples.
Mr. Balogh,
What?
your friend is still pushing the car out. He's still increasing out.
You have to push out to keep it going. Yeah, okay. All right, so there's our sort of our template and our step 2 choices, right? So the reason that we did that whole table was to sort of offload a little bit of the conceptual work here, right? There's still a lot of stuff that we have to determine, right? We have to determine how flux is changing in step 1. Step 2 hopefully becomes a little bit automatic, so that step 3 we can apply this right-hand rule. There's a lot of concept coming together here, which makes this difficult. There will be a reason for all of this, a direct application to your lives, I promise. You just got to hold on, okay? All right, give me a magnetic field into or out of the page. I heard out first. Coil enters from top, bottom, left, right. Left. So coil is right here, and it's coming. No, it's not. It's leaving. Okay? All right. So let's apply Lenz's law, do all that stuff. First step, before we can apply Lenz's law, what do we have to determine? Change in flux, right? What is the change in magnetic flux? Increasing or decreasing? How do you know it's decreasing? Leaving it behind. The magnetic field is becoming smaller. Okay? It's decreasing, and which way is the field pointing?
Oh, sorry, out.
The field is pointing out. Okay, a decreasing out is met with a increase out. And so which way do we put our thumbs? Do we follow the step 1 direction or the step 2 direction? Step 2 direction, so our thumb goes where? Out of the screen, and our fingers wrap around. Yeah, some places use anti-clockwise instead of counterclockwise, right?
Yes,
okay,
right.
but okay. Here is a coil of wire. I'm holding a magnet in front of the screen. I don't have a magnet with me. We'll use this, okay? I'm holding a bar magnet in front of this screen, okay? The south end of this bar magnet is closest to the screen, and I'm going to bring the magnet closer to the coil. Do you get an idea of what's going on here? South end is pointed towards the screen, and I'm going to move the south end closer to the coil. What is the change in flux? Turn to your neighbor, see if you can't figure it out. Increasing or decreasing, and then into or out. Figure it out. Go. Okay, that was my very lame attempt at trying to draw a 3D image of what the heck's going on here. Okay? All right. Is the flux increasing or decreasing? Why is it increasing? It's because the magnet's getting closer. Okay, right? So we can do that. Okay. Now the question is it increasing into or out? The south pole of a magnet is where magnetic fields enter, right? They go into a south pole, they come out of a north pole. They don't begin and end because they're closed circles, right? So all the field has to be flowing into the end of this magnet. All the field lines are coming like that, right? So with the 2D version, right, if our thing's coming closer and all the magnetic field is kind of wrapping around and going into the end of this, so what direction is the magnetic field pointing? Out. And in the animation, if I could animate this, we'd see that, and then we'd see that, and like we would get more and more and more and more, right, of these dots. So it's increasing out. Okay. Second step should be easy now. Now that we got our table, we got increase out. Increase out is fought by an increase in. So for the third step, right hand rule. Okay. So this is now going to be pointing into the screen, and it wraps around clockwise, doesn't it? Okay. Same picture, but this time I pull the magnet away. I want you in pairs and groups to figure out what direction the current is in the coil if I pull the magnet away. Go. All right, so you have a choice. There's two answers to this question, right? And only two. What are the two possible answers for the direction in the coil? Clockwise or counterclockwise? Okay, 50-50 chance. We want to up the odds, right? So we have to determine how the flux is changing. How many of you said the answer is clockwise by a show of hands? Okay, how many of you say it's counterclockwise? And the rest of you aren't sure, you're totally lost? Good, okay, no, totally lost is correct. Okay, this is new, this is the first time you're seeing it. You're going to practice this a lot. You're going to need to, okay? What's that? Well, in homework I've only given you like what? 3 or 4 conceptual questions? You're going to want to practice more than that. Quiz each other. All right. Increasing or decreasing? Why is it decreasing? Because the magnet's moving away. What direction is the magnetic field pointing? Still out. We didn't change. The south pole was still the closest to the coil. Okay. So how do you find a decreasing out? You increase out. So which way do you put your thumb? Out. Which way does it go? If I put my thumb out, my fingers wrap around counterclockwise.
Sorry, the tiger.
I wonder where we've seen this before. Okay. The current in the wire decreases. What direction is the current in the coil? Got a wire, got a coil, right? The current flowing upwards, okay, decreases. What direction is the current induced in the coil? Okay, step one. What do we do in step one? Got to figure out the change in flux through the coil. Is the flux increasing or decreasing? Why is it decreasing? If the current goes down, then the magnetic field generated by the wire goes down, right? So we know that the magnetic field through this coil will be decreasing. Can't spell now. Never could. Okay, but what's the other important part to determining the change in flux? The direction the field is pointed in the first place. Well, how the heck do I know what direction the field is pointed? I have to use a right-hand rule to find the magnetic field of this current carrying wire. Which hitchhiker am I going to use? What is my thumb for the finding the field of the wire? It's a straight wire, so I'm going to use my straight thumb to be the current. The current's pointing up, so my fingers over here by the coil on the right side of the wire, which way are my fingers going? Into the screen. So the field, well, everywhere around this wire is into, isn't it? Okay. On the left, it would be out, but I don't care what's going on the left because there's no coil over there. Okay. So thumb was up. Now notice, I had to use a right-hand rule just to do step number one. All former right-hand rules apply. Okay. So we know it's decreasing into. So step number two. So we're going to increase into. Sometimes I draw this like this. Right? Just as a shorthand, if I'm doing a lot of these, and I just keep not wanting to write decreasing and increasing, right? Sometimes I use D and I, decreasing, whatever, right? Okay, and so step three, the hitchhiker rule, but the other kind, right? Okay, my thumb, instead of being a current, is now the field pointed into. Fingers now wrap around clockwise. Go back and play that portion of the video a lot. Okay. See if it can't start sinking in. Come up with scenarios. There were websites that had flashcards of these, like it would just throw up a thing and then the clockwise or counterclockwise or whatever. Do I still have? Second, I'm remembering something. I thought. Yeah, the problem with Quizlet is it tends to be for high school. Yeah, okay. Yes. At the risk of breaking everything. What is this? This is Canvas. Under chapter 22, Lenz's law, practice problems, and Lenz's law, practice answers. I remember this from last semester. I found something, okay? And instead of giving a link, I just copied the content because websites die, right? And the Wayback Machine sometimes, I gave the reference. Good, Mr. Balogh, giving the reference, okay? So what I did is, and you'll see a bunch of artifacts on here. I covered up the answers, right? Because the original document had all the answers, right? But as you can see, what is that? It's 4 by 5. There's 20 on there, 20 on there, and 20 on. You've got 60 practice problems, right? Okay? Of different like orientations of loops and coils and things like that, right? Moving stuff in and out. Coils and wires and things like that, right? So you can go through and try these, okay? And what I did is I also provided in a different, whoops. You guys don't usually get to see that. Now all my secrets are known. I provided the answers version, right? Okay? So you can grab both. I highly encourage you to not look at the answers. Try a page of them, right? Write out the direction you think that those currents are forming, and then pull up the answer sheet and only look at like the first page, right? And grade yourself. And then go back and figure out why you got it right and why you got it wrong, right? Okay? So I have that resource for you to try a bunch of these things. Okay, now that I've broken the universe, technologically speaking, can I get back to the, no, not that one, this one. Because I want to play for you this video, which, again, hopefully gives you an idea of kind of what's going on with Lenz's law. There's always something that breaks. Always, always, always. There we go.
Current flows through a coil of wire whenever the magnetic flux through it is changing.
That's a decrease.
The current flows one way if the flux decreases,
I just said that.
and the other way when the flux increases.
The arrow at the middle is the field created by the coil. I think. No.
But the current induced in the wire
No, it was the
also
it was the field from the magnetic field, sorry.
whose direction depends on the direction of the current. The flux created by the induced current always opposes the change in the external flux. This rule is known as Lenz's law. The net result of both fields added together is to slow down the rate at which the magnetic flux through any circuit is able to change.
Oh, nice music at the end. Did you catch what it said there at the end? The last picture was when you superimpose both fields together. The field externally that's changing, that's causing all the problems in the first place, and the response to the coil. When you add those two fields together, overall, you have a situation where nature will always try to slow down the rate of change of magnetic field in a coil. Lenz's law is a braking mechanism, right? It tries to slow down changes in magnetic flux. And we can take advantage of that idea and do some really neat applications. So let's start the applications. If I can get this to work.
Mr. Balogh, all those lines going away, was that decreasing the magnetic?
That was the external field, right? And as the fields kind of moved out, they spread out from each other. That's a weaker field. Remember, the closer magnetic fields are together, the stronger they are. Yeah, it's weird. Physicists have weird ways of thinking about how the universe works. Okay, so we're going to. This is going to be weird. I'll give you that. It's going to start out weird, and then it's going to be cool. Okay. Let's say that I have like a railroad track, okay, two metal bars, conductors, okay, and I lay a third bar across it. And then I'm gonna like electrically connect, that's a resistor, but it doesn't matter, okay? Electrically connect the two bottom tracks together, okay? And then this bar that's sitting on top of the two tracks is free to roll or free to move along those tracks. But there's an electrical connection such that I can form a complete electrical circuit all the way around, okay? And let's say there's a magnetic field. Doesn't matter if it's into or out, okay? Let's say there's a magnetic field between the tracks. And we're going to go and we're going to grab this bar and we are going to move it, okay? We're going to apply a force to it, okay? And it's going to get some speed, right, because of that application of force, right? What's going to happen? Does the flux increase or decrease? Faraday's law. Now you know what the minus sign means. The minus sign means is Lenz's law, which means go do all of that stuff, right, to get a direction, clockwise or counterclockwise, right? Okay, so from here on out, I can drop the minus sign because if I'm just going to calculate the strength of the voltage and current, then I don't need to worry about whether it's going clockwise or counterclockwise, right? So let's calculate this change in magnetic flux. Something is changing. What's changing? Is it B, is it A, or is it the angle? It's not B. It's not the angle. Is the coil rotating? Remember, my coil is this sort of weird shaped thing right here, right? The area is changing. I told you there was one case, right, where it's conceivable that you could change the area, right? Okay. So the delta is being applied to the area. The magnetic field strength is staying the same. And the angle here is 0 degrees. So I'm just going to drop the angle, okay? And it's a change in area. But now we need to be able to write down what this change in area is, okay? Well, to get the area of this loop, right? I need like a length. So we'll call this L. Right? So how do we find an area? It's length times width, right? When we know the length is L, what's this width down here? It's the distance. But how do I find this distance if this thing's getting bigger? Distance is equal to velocity times time, isn't it? So this width will be equal to whatever the velocity is times how long it's been pulled. So my area is now L times V times T. What's changing? I've done this. Hold on a second. Let me back up. I'm going to call, I got too excited. I'm going to call this X as a variable distance, right? Okay. We know that eventually it's going to be V times T. I let the cat out of the bag too soon, okay? So if our area is length times width, then the delta is being applied, right? This delta isn't applying to L, it's applying to this width, so it's applying to the X, isn't it? So it's L times delta X. So now I plug this into Faraday's law, right? It's negative N. There's only one here, right? I'll leave N in case we got more than one loop. And then it's B times delta, B times L times delta X all over delta T. So the delta T came from Faraday's law, right? My change in flux was B times delta A, and delta A is L times delta X. Okay, now that I've told you the answer, what is delta X over delta T? Right? So this is negative N. We usually do BLV, okay? And then we'll often just drop the N and just say BLV. This is called motional EMF, I think it says at the top. This is the voltage that's created in a conductor as it moves through a magnetic field. If we grab this bar and we pull it along the track, then we will get this voltage. The voltage is higher the faster the velocity is, right? But we can reverse this. We can push on the bar and create voltage. We can have voltage create motion. It goes either way. And it turns out that you don't even need the track to be there in the first place. You don't even need the full coil to be there, because if you move any conductor through a magnetic field, it will generate a voltage. It may not generate a current because there's no coil for it to complete, but the voltage will happen. Case in point, airplanes. What are airplanes? Well, they're airplanes, Mr. Balogh. They're conductors moving through magnetic fields. What magnetic field? Earth's magnetic field. So if an airplane flying at 540 miles an hour, which is 800 kilometers per hour. I apologize for what is about to occur. That's an airplane top down. Okay? And let's say the Earth's magnetic field, we're flying in the northern hemisphere, so there's a downward component, okay, in the northern hemisphere. Because in the northern hemisphere, what magnetic pole is it? South, and magnetic fields go into south poles. So in the northern hemisphere, the magnetic field points north and down. Okay? In the southern hemisphere, it points out and north. Okay. So as it flies through the magnetic field, it's moving along at speed v at 800 kilometers per hour or 540 miles per hour or 0.85 to 0.9 Mach at cruising altitude. I am a nerd. You want to guess the EMF that's generated across its wings? Standard wingspan for like a Boeing 737, which is, what is that, like, is it 18 meter wingspan? Something like that. I guess I'm not that much of a nerd. You would think it would be huge, right? If you do the calculation, which is B times L times V, magnetic field of Earth, length of wings, and how fast the thing is flying, this actually only turns out to be half of a volt. It's not very big. Why is it not very big, even though it's moving very fast? Because the magnetic field of the Earth is pretty darn weak. Okay? Actually, planes do generate quite a bit of voltage while they're flying. Okay? And that is because of static electricity buildup on the airframe as it flies. As it flies through the atmosphere, dust particles, water molecules, all kinds of things can build static electricity, kind of like Van de Graaff generator almost. And so one of the first things that has to happen after a plane lands on its rubber tires is, as it pulls up to the gate, okay, and before they open the door, some person who lost the party that morning has to run out with a plug and insulated gloves and plug the plane in. It does two things. It provides ground power so that the plane's engines can be turned off to save fuel, right? But still power the air conditioning and the emergency stuff and all that kind of stuff, right? Okay. But the other thing it does is it decharges the airframe. It grounds the airframe so that people don't get static shocks when they jump out.
How bad would the shock?
Pretty bad. It kind of depends on atmospheric conditions. Like if it's raining, it's 0. but if it's Las Vegas, it's high, right? Like it depends on how dry the air is and all kinds of stuff. So, yeah. There's no grounding chain on an aircraft. There are grounding chains on, if you've ever watched a semi-truck going up and down the road and they're carrying fuel, you'll see a little chain or a wire that's bouncing along the ground. Okay? And you're always like, well, the idiots forgot to put this chain. No, that's there. That's safety. What is the chain doing? Grounding the vehicle constantly, right? So that no excess of charge builds up. So that if there's any fuel escape, there's no way for ignition source from the truck, right? So that's what's going on there. All right. Okay, so let's reverse this. Instead of an airplane flying through the air, I've got a coil, okay? This coil is attached to the standard main, okay, 120 volts AC. I've got a switch on the front that, I don't know if you can hear the buzz, but what it does is it basically takes this coil and connects it to the wall, right? So in this coil, I'm going to have alternating current. So current's going to flow one way in this coil, and then it's going to turn around and flow the other way, because that's what AC is. It's this bouncing back and forth current. In the United States, the frequency of the alternating current is 60 hertz, which means 60 times per second it does a complete sine or cosine function. That means that 120 times per second it reverses direction. Because in any back and forth, there's two changes in direction, right? So 120 times per second, the magnetic field is going to change its direction. Okay, up, down, up, down, up, down, up, down. I'm going to take a cylinder here. Okay, this is a metal aluminum cylinder. It is not magnetic. This is a strong magnet right here. It doesn't stick. Okay, I'm going to put it on here. Okay, so what we're going to do is we're going to change the magnetic flux through that coil, right? This is a coil, isn't it? Cylindrical coil. I'm going to change the magnetic flux through that coil very quickly. Okay? It's going to be increasing up and then it's going to be increasing down, and right? And really, really fast. Okay? We've learned that the coil will fight the change, right? And not only will it fight the change, changes in magnetic flux can cause motion, right? Motional EMF. I can create motion from these changing magnetic fluxes. I can generate electricity. I can do all kinds of stuff. This case, it's going to generate motion. Here we go. Right? And a pretty significant amount, right? Okay? So, watch that again. I never quite hit the ceiling in this room. Okay? However, if I had some liquid nitrogen and I cooled this off, it wouldn't become a superconductor, but the resistance would go down. And with lower resistance, you can poke holes in the ceiling tile. Okay? All right. So let's back up, right? Why is it getting launched?
Hit the ceiling.
Depends on how quickly you do it. How? Why? How? Motional EMF. I'm causing this change in magnetic flux, and it's giving rise to this propulsion, this velocity, right? Okay. Video gamers, what is this?
Oh, a rail gun.
It's a rail gun. Okay. Okay. Right? I can, right, shoot projectiles not using any gunpowder. Only electricity. The Navy looked into making rail guns for ships, and it's just not going to work. All right, for lots of reasons we won't get into now. This is a brass. So this is exactly the same as this aluminum one. Same radius, okay, same height, everything, but brass is heavier. Please verify for me.
Oh, much heavier.
Imagine probably like twice at least, right? Okay, okay. So let's see what happens with that one. Right? Half as high, right?
Yeah.
So same amount of like force applied, same amount of oomph. It's just that it's twice as massive, so it only goes twice as high. half as high. Okay. Now I've got one that's half as high. Right? Same radius, same material. Okay. We know that this one pretty much hits the ceiling. What's your prediction for the half as high one?
Second floor.
Second floor? Should we take out the biologists?
Why? Okay, half as high.
Why only half as high?
Half as
Half the number of turns. N for this one is smaller, right? There just isn't as much circulation that can take place, okay, in this one. All right, back to the
Is it not Oh, there's a hole in it.
this one's got a, do you see the gap? So, yeah, it's not a coil.
So there's no turn.
There's no turns, right? Okay, there's no complete circulation here. So while voltage gets generated in it, no current gets generated in it, right? This is a coil. It's lots of little tiny magnet wire, 1,000 turns or something like that, okay? Connected to a light bulb, right? I'm going to put this in, here where the magnetic field is being generated, right? Okay? So this is not electrically connected, it's only magnetically connected. Wireless power. What is this? It's MagSafe, right? Okay, put your thing on the charging pad. This is it. This is how your toothbrush charges. Okay?
With like distance, how much more power would you need?
A lot, okay? You end up microwaving flesh in a room if you try to have like that. That's why we don't have everybody's like, Mr. Balogh, why do we have wireless power yet? Nikolai Tesla, blah, blah, blah. Okay. We do have wireless power. What's it called? Batteries.
Oh.
Right? It's called batteries. Before I let you go, let me show you one more thing. And then I'll bring this one next time. These are harder to move, okay? Light bulb, magnets, down inside magnets where you can't see it, coil of wire. Coil of wire attached to crank. I'm going to turn the coil of wire in the magnets. What am I going to get? Light. What is this? It's a generator, right? This is how PG&E makes all the stuff, right? Whether we're turning coils or changing magnetic fields, all that matters is that a change take place. Once the change takes place, we can do anything. I'm going to give you more examples on Tuesday. We'll explore magnetic fields on Monday in lab.